Hello, everybody. Welcome to the closing keynote and lightning talk session for the Conference in the Cloud. I would like to introduce everyone to Jonathan Worthington. He is a team lead at Edument in Prague. They work on developer tooling and compiler technologies. Jonathan is also known as the architect for Raku and more VM. He is a great lover of Indian food and beer, and he's currently trying to claim bragging rights for visiting every train station in the Czech Republic. Jonathan?
Hi, hi everyone. It's great to be here, and so it's actually about 10:30 p.m. Here in Prague, and just before I came on, there was actually a huge barrage of fireworks, which were very loud. So I'm kind of happy to have just missed that. I decided to do a recording of my talk because I'm not quite convinced that 10:30 p.m. on a Friday, when I've been debugging virtual machine guts for the week, is when I'll be at my most coherent. So we'll do that, and then afterwards, I'm happy to take any questions that you may have from the talk, or anything else you fancy asking me.
So good afternoon, folks. Thank you for joining the session. I'm Jonathan Worthington, and today I'm going to be talking to you about Raku AST. This is something that is going to be a foundation for putting macros into the Raku language, but as we'll be seeing in the session, it's actually quite a lot more than that. Now, from this title slide, you might have actually two pretty good questions already, so let me answer those. The first is, what on earth is an AST? And this is short for abstract syntax tree. If you've done some HTML and JavaScript programming, you probably will have come across the document object model. This is an object-oriented model of the HTML document. So often we're not dealing with the HTML as a string. We instead can traverse the various elements and their attributes and their child elements using an object model and modify them and so forth. So what we're really talking about here is some kind of object model to describe a program in the Raku language. Your next question might be, who on earth am I? Why am I talking about this? Why am I interested in this? So I'm currently serving as the Rakudo compiler architect. Rakudo is the compiler that most people use to run their Raku programs. I also founded and continue to be architect of MoreVM, which is the runtime that people are using to run their Raku programs too. I've also got an interest in concurrency, and that led me to help out with the concurrency design of the Raku language. And I also founded Crow, which is a set of libraries for building actually mostly web applications in reality. It's more general than that, but people mostly use it to build web services, HTTP applications of various kinds. And you could sort of see it as being a service framework, a web framework, depending on which modules of it you choose to pull in. When I'm not doing those things, I am a team lead at Edument. I lead the Prague office there, and my team is responsible for building the comma IDE for Raku. As well as that, we do a lot of consultancy around the IntelliJ platform. That is the platform that we've built the Raku comma IDE on top of, and it's used for IDEs for quite a lot of other languages too. And we also do bits of compiler and language design consultancy. So here are the topics that I'd like to cover today. First, I want to talk about the motivation for adding an object model form of the Raku language to the language specification. So today we specified the syntax, we specified the semantics, and what I'm proposing is that we also specify really a document object model, an abstract syntax tree form of Raku. And we have that covered as part of specification tests, and language users can depend on that. Assuming we're doing that, I then want to discuss, well, how do we design such a thing? And it turns out that when you start looking at this, you realize that actually the compiler also needs to really get quite involved in the new AST form if we're going to do this in a good and efficient way. And so I'll explore the various design considerations there. I'm already working away at this, and I want to talk a bit about the progress that's been made implementing Raku AST so far, and then I'll close with some notes on the impact. So what can you expect in terms of compatibility when we ship a Rakudo with Raku AST at the heart of it instead of the current compiler front end? Will there be performance impacts and so forth? So let's start out by looking at the motivation. Now, of course, for a lot of people, it'd be cool to have macros. This is the first thing they see or they start thinking about when I talk about this. Well, it's not really entirely true. At least it wasn't my primary motivation for this. Of course, it's important. Macros are pretty great, but it's just one reason for all of this. But let's actually talk a bit about macros anyway to see why an AST is an important part of having good macros. There's more than one way to do macros. There's certainly more than two ways, but I'm only going to really talk about two of the ways, just to contrast them. One of them is textual macros, and if you've programmed in C, you'll probably have come across these. The idea really is that they operate at a sort of level where they don't really understand the structure of the program. It's not really fair to say they operate at the string level. It's more like they work at the token level. So we've already broken up the source code into, this is an integer, this is a keyword, this is a parenthesis, this is an addition operator, and so forth. So they're not really string manipulations, they're token manipulations. But in terms of understanding larger language constructs, they just don't. They're before that. So you can have all kinds of fun with textual macros. And for example, if we decide that really what C needs is to have less curly braces, then we can define the word do to be replaced with the left curly brace and the word end to be replaced with the right curly brace. And then we can write our C code like this. And that kind of goes to show you that really the structure is not a concern here. Even though we, in our minds, see these curly braces as part of this one and the same thing, we could actually just define do and then write the closing curly, for example. It's no problem. Now, while they let us do all sorts of things, we have to be very, very, very careful. And there's all kinds of things that you learn as you learn to program in C. Some of them the hard way, at least if you're me, that you should do. So here we decide that we don't want to have magic numbers in our code. We want to write something that nicely captures the size of this very imaginatively named thing, object, and we say, well, it has a header and it has a body, and the size of the whole thing is its header plus its body. So we write this, and then we go and we write some code like that. So we say, well, we need to allocate some memory for the things. So we take the number of things and we multiply them by thing size. And this all looks completely fine so far, at least if we forget about how we define the macro. Of course, the compiler knows full well how we define the macro. It says, well, thing size should be replaced with thing header size plus thing body size. So we'll do this. And those actually really boiling down to those constants there. So we end up with this. And oops, because we almost certainly did not expect that multiplication to bind to just one part of the thing size. We really wanted to multiply num things by the total size, including the header and the body. So an alternative is what we might call AST macros, and Lisp made these famous. Macros operate, in this case, on the parsed program. And by parsing, I mean we take the text of the program, we not only break it up into the tokens, but we then arrange them to say, for example, well, multiplications happen ahead of additions. And we have some understanding of the program structure. So here is an example of how we might do this. And we just define a macro called thing size. I haven't done all of the other bits there. And that backtick there just says, well, we would just want to quote this bit of code. You'll see that operators here actually come first because there's a very regular structure here, which is function name and then arguments. So then when we want to apply the macro, then really it's just like a function call, except the function call is made by the compiler at compile time. And if we gave this arguments, what it would actually receive is an AST that represents the program. But because this is seen as a function call, and we splice the result, which is also you could see as an AST node into the resulting program, we're guaranteed that this is going to come out correct. We're not going to get the strange behaviors that we might see if we're working at a token level. Of course, there's reasons C went the way it does. There's some good engineering trade-offs that were certainly very important at the time that the C language emerged. In fact, C is described as really a set of staged languages where you apply one set of steps and then you apply the next set of steps, and one of them is pre-processing, and that kind of makes sense if you're in a more constrained environment. So anyway, this is not really to dump on languages. I don't like to do that, but to say, well, given the world we live in today, I think that actually we're in a much better place if we take the Lisp route. Now, Lisp is conceptually very beautiful. It's a language for processing lists, and programs themselves are lists. So you get a very natural representation of the program, and then you get all the tools to manipulate it that you would want. Lisp really means list processor. So what about Raku? It's quite clear that Raku's syntax is slightly larger, I guess. Actually, to be fair to say, it's a much greater diversity of syntax, and therefore that means it requires a much more complex model. But even if the model of the syntax is more complex, we can still actually hold on to a lot of the advantages. A Raku macro really is, or will be, just a function that is called at compile time. So the compiler says, well, I've got the arguments here, I've passed them, I've got some tree, some object model representing the arguments. Now I'll call the macro and I'll pass those in. And the macro will return some other representation of a piece of program, and that will get spliced in just as a child node of wherever this call was. So we get a lot of the same kind of benefits. Really, it's doing AST macros. So here's an example of how we might define a macro in Raku. The macro is called while defined, and it takes two arguments. And the thing to keep in mind here is that these are not arguments that are going to receive data. They're actually going to receive objects describing the program. So the compiler calls this, and it calls it basically after it's passed all the arguments, which is going to be around the closing curly brace of this lambda here. And those arguments are going to be Raku AST objects, objects that model the program. So there'll be one that sort of says, well, this is applying a postfix, which is actually the shift method call, and that's being applied to the variable a, and then the body will be the lambda expression there, and well, it won't be the lambda expression, it'll be an AST node describing that we have a lambda expression. And then we could at this point go and produce a result by calling .new on various object types. So we might say, well, make a RakuAST statement while loop node and pass it in something that is an assignment expression to this temporary variable declaration and so forth. But there's actually a nicer way, which is this quasi-construct, which really is a way of quoting a code. Essentially, we say to the compiler, well, what I'd like to do is to write some code, but please don't compile it, just turn it into an abstract syntax tree form, and then just keep hold of it. And a little bit like when we, if you think about having a string, and you do some string interpolations, and you then define a closure around that. Then you pass arguments into it, and that is then used to produce an interpolated string. It's a little bit like that here too. These triple curly things allow us to interpolate over bits of AST into the code. So when we invoke this macro, or when the compiler invokes this macro at compile time, it'll pass the AST for a.shift, and we'll insert that into the AST that this quasi is producing. You can almost think of a quasi as like a little templating language for Raku code. The same thing happens with the body, and then what we end up with really is something like this. It's a bit of code that, well, an object graph representing a bit of code, I should really say, that has had the various variable parts, the quoted parts, spliced in. And then we take that and we insert it in place of the macro call, and we have that. And then the compilation goes on just as usual, as if nothing really changed. The only thing that is a little bit worth noting here is that this $temp here will not actually introduce a $temp symbol that you can visibly see. This is all a matter of what's called hygienic macros. I won't go into that right now, but the idea is that we sort of have a renaming or a name generation process that takes place as part of the process of instantiating and inserting a macro result. So I think at this point we can say, well, okay, we don't just want macros, but it's really cool to have AST macros, and to have those, yeah, we need some kind of AST that is something we can pass around. But there's actually more than that. This is some code that I wrote a while ago. It's using a module called Crow Web App Form. The idea is you define a class, you compose in this role, and you basically are describing a web form. And we can apply various traits here as well. And one of them is validated. And in is validated, we specify some kind of condition, and we then have a message that is the thing to tell the user about if they give input that we don't consider valid for some reason. So this trait handler is running compile time. And the idea of them is they provide a way in that we can hook into the compilation and attach extra bits of metadata or do various tweaks to meta objects. But actually, if we could get hold of the AST of the arguments to the trait, then it would be possible to compile the Raku regex into something that we can use in the HTML5 pattern attribute. So that means we could actually be defining a client-side validation here as well, at least when the regex is something that's sufficiently simple that we can translate. Notice here that we would not have to go and parse the Raku source for the regex. We'd actually already be given an object model that describes it. There's also a load of modules that basically produce Raku code. Some of these are mine, some are not. So, for example, the ECMA 262 regex module takes regex syntax, the JavaScript regex syntax, which is used in the JSON schema specification, and compiles it into a Raku regex so that we can evaluate JSON schemas. File ignore does the same kind of thing, except for git ignore style patterns. JSON mask and JSON path actually don't really compile. They interpret the masks and paths, but could be much more efficient if we compiled them into Raku. Now, what does that look like today? Today, modules that want to compile into Raku code and pass it off to eval kind of look like this. They're doing strings. They're building up various bits of text, program text, hopefully getting it about right. And eventually at the top, we end up with a full program string that we pass off to eval. So yeah, first of all, strings. I'm a compiler writer. I'm not very into strings. Strings are a very weak model of anything. But more concerning than my kind of knee-jerk dislike of strings, how do we know that this code is well formed? When do we find out? We find out when we eval it. If we've made any kind of mistake, it'll come up all the way at the eval, and then we'll have to trace back, well, where did this character come from, what produced it, and so forth. More scary than that, though, is not just that the program might be badly formed, but it might be evilly well formed. Injection attacks, whether they're path injection or SQL injection or so forth, basically all revolve around constructing languages incorrectly. They happen when we have a string and we think of it as data, but it contains things that will actually have semantic meanings in the target language. And whenever we build languages by constructing them out of strings, we're at risk of this. So we kind of like not to do that. The other thing is it's all very wasteful. So we're taking our time to turn this parsed structure into a string only to give it to the Raku compiler, and then it will take it and turn it back into some kind of graph again so we can get on with compiling it. It would be quite nice if we could avert all of that work. So they could produce a Raku AST instead. By building up the object graph, by using quasi-quoting if that's more convenient, and so forth. So what we're really saying is, well, not only macros, but it'd be cool to have various ways of accessing a Raku AST at compile time, even using it as a compilation target for modules that generate code. But there's even more that we could do. What if we want to build a linter? What if I want to build some kind of fancy type checker for Raku? That maybe takes a bit more time, but perhaps finds a few more things to complain about. Or what if we are doing some kind of domain-specific logic, and we want to have various compile time checks? So for example, we have the Crow HTTP router, which is widely used for building the routing part of HTTP applications. And it'd be kind of nice if we could detect various mistakes, like, oh, you defined two routes for the same, or two route handlers for the same route. Or this thing that you have written in the thing that matches the route could never possibly match. Those aren't things that we would have as general things falling out of the language syntax and semantic checker. But we can actually add them in at compile time by doing some code analysis. So all of these things, traditionally, the tools get built with their own parser. Often, I guess someone builds a parsing module, and then they use that. But they have to do that work, and that means that they can get out of sync with new language features, or they can end up with having their own bugs. They can lack some bugs the actual compiler has, but they can introduce a few new ones and so forth. So they could just consume a standard Raku AST and say, well, I just want to actually insert this extra compilation phase that does some linting and type checking and so forth. So at this point, you can say, well, it'd be cool to be able to produce and consume Raku code in all kinds of different scenarios, and having a standardized AST will let us do that. Really, this must be all right. But actually, this presents another interesting opportunity, because Raku hasn't really changed its front-end compiler architecture in about 10 years. That's quite a long time, and obviously we've learned quite a bit in that time. So really, I see this not as something that we're going to add. Instead, really, we're going to build RakuAST, and we're going to rebuild the rest of the Raku front end around it. That sounds kind of, quite a big job, quite a crazy job. It's worth pointing out that actually, when we talk about Raku, when we talk about the compiler, what we're actually talking about is not really just a compiler. In fact, a huge amount of the code is implementing the meta model. That's how the objecty things work. It's implementing the standard library, the built-ins. In fact, the majority of the code is not really tied up with compilation. So really what we're saying is we're going to rebuild one part of Rakudo. But that part is of course quite an important part. It's the compiler front end, the thing that goes from source code to producing some kind of intermediate form that we then can turn into, say, more VM bytecode. But really we're going to be rebuilding that as part of this Raku AST project. So I think this is going to be pretty great. It'll open a lot of doors. I think it'll get us a much better compiler architecture. The question is, how will we get there? So let's move on and take a look at the design of Raku AST that I'm working on and how this affects the rest of the compiler that is built around it. First, a recap on how things work today. We have Raku source code. It goes into the compiler front end, and what comes out is a cast tree, and the AST in there is indeed abstract syntax tree. This is a relatively low-level abstract syntax tree. It's proven pretty successful at virtual machine abstraction by letting us run Raku code on both the more VM, the JVM, also JavaScript. So it's good at that, but it's also quite low level. And that means that it's not really a very comfortable thing for the Raku language user to work in. The concepts in it are not really naturally mapping to concepts that a language user of Raku would understand. The other thing is it's not very convenient because this AST doesn't really fit within the Raku type system or its various conventions, so it's not very convenient to use either. The front end consists of the parser, which cares about the syntax, the actions, which care about the behavior, that is to say, the semantics of the program. They do that by taking various language constructs and saying, well, this is how they compile into cast. And then we have the world. The world is involved in declarations. So when we have a variable, that creates a declaration. When we use a variable, we need to say, okay, is this variable in scope? The same for subroutines, types, and so forth. Also, when we declare a class, then this does some mediation with the meta classes too. So it says, okay, we need to create a meta object to represent this class, and then we add the methods and attributes into it and so forth. So generally, you could say that the architecture is one of large components that each know some aspect of compiling the language as a whole. The parser knows the whole language syntax. The actions know the whole language semantics. You can see we have quite a lot of those. The world knows about all of the various declaratory aspects of the language, and the optimizer about optimizing all the language. Error reporting is kind of scattered throughout them. So the parser, in theory, just reports syntax errors, but I think actually the design is more like, well, we report the error in the place that most immediately makes sense and has the information most conveniently available. There isn't really a sense that the only things the parser reports is syntax errors. This is a bit of a problem for Raku AST because, of course, there's errors in it you can only make when you have a string source. And if you have a tree or document object model for the language, you just can't create that problem in the first place. You can't have a mismatched closing parenthesis or something like that. That the concept just doesn't exist as a problem at the document object model level. So we need to take a good care of that as well in Raku AST, because of course those errors don't need to be reported. They don't make sense against a document object model of the program, but a lot of things do. So there's nothing to stop you having an undeclared variable, for example, in the AST form of the program, and we still need to detect that. So the way I like to think of the Raku AST design of things is that a particular node is an expert on a particular language construct. It has all the knowledge about that language construct except its syntax. And that kind of makes sense because really syntax is just another way of constructing a Raku AST. It's probably the most common one that people use, it turns out. But really, it's kind of a step before we have this, and that's why the syntax would lie outside of it. But otherwise, it knows pretty much everything about a given language construct. So it knows about the semantics, and that is again done by defining how the node compiles into cast. It knows if it makes a declaration, if there are any meta objects that need to be produced, things like routine objects or class meta objects and so forth. It knows about symbol usage, both explicit, so if I have a variable $foo, then obviously I need to look that up, but there's also implicit symbol usages in Raku. So if I write $0, which is the zero for capture, there's no $0 variable. We don't want to look that up, but implicitly we are wanting to do lookups of $/, the match variable, and also we'll want to be looking up the array index operator. The nodes will also know about check time, that is semantic errors. They'll deal in sync context handling. So if some things need to compile differently, depending on if they're in some kind of void context or at statement level, and also optimization. So if we think about the for loop construct, then it would have a Raku AST node. It's actually called RakuAST statement 4, and the semantics of that are to obtain an iterator and then invoke the block for each thing the iterator gives us. It doesn't really make any declarations or meta objects or look up any symbols. It does, however, care quite a lot about sync context, because it knows that it doesn't need to build up a result list if it's at statement level or if it's being sunk. So it then can propagate that so that we also know we should discard the last value inside of the loop. And it also will have some optimization knowledge. So for example, if we loop over a range, we don't really need to go and do the whole iterator dance. Instead, we can just compile it into essentially really a while loop that invokes the block with the integer value. So when we put this into the compiler front end, a lot of the complexity moves into these Raku AST nodes. And really the parser is left a little bit simpler. It's not going to change that much, but it gets a bit simpler. It only needs to report syntax errors. The actions get massively simpler because their job now is just mapping the parse tree into Raku AST. That's actually a relatively simple mapping by this point. So what about modules like my regex one, where I have the JavaScript regex syntax and want to compile that into Raku code? Well, I won't do that anymore. Instead, I'll compile it into RakuAST. But the structure looks very similar. We have a parser, we have some actions, and we make RakuAST. It's just that this time the grammar is one for JavaScript regexes, and the actions are transforming from that into the Raku AST nodes that describe the regex. So we don't do any source generation at any point now. We just produce this abstract syntax tree. So really, we can say that Raku AST nodes model language constructs. For example, there's a node for a parenthesized expression. Often just putting something in parentheses is pretty much free of extra semantics. For example, if I just wrap something in parens because I want to get an addition done before a multiplication, there's no real extra semantics there, but we still model the fact that these exist. This actually comes up quite useful when it comes to compiling argument lists, because there, if we have a fat arrow pair and it's directly in the argument list, then that is a named argument. If we wrap it in parentheses, it just becomes a positional argument of type pair. So these things actually matter, and this does turn out to simplify the compilation of argument lists as well. One of the really important principles is that Raku AST nodes should work just like any other Raku object. They shouldn't really be very special in that sense. So they should fit within the type system. We should be able to do things like multiple dispatch over them. We should be able to destructure them with signatures. That means taking out different parts of the tree that are nested within it. That's actually very convenient when doing this kind of programming, because often when we do tree manipulations, we want to know, what sort of things does this node contain within it, and to extract them. And doing that declaratively with a signature is pretty nice. They should also be introspectable, so that we can explore them in the REPL, so that IDEs like Comma can use that to provide autocomplete on them. And also, I would like RakuAST to be very easy to construct. You just call new on a node. At most, you might have to make some child nodes, which are required, but there's no sort of heavyweight context objects or compiler state objects that are needed. You might need those for later stages, like actually compiling or doing reference resolution, but the AST construction should be pretty straightforward and lightweight. I also realized that we can use types to encode valid syntactic structure. So if we say that, when you construct a statement list, then the things that are in it must be statements. Or if we have a signature, then the things within it should be parameters. One of the other nice things that falls out of this is that if we have macros that only make sense on certain kinds of syntactic construct, that can be done just by putting type constraints into the macro signature. Further, the compiler can even actually map those back into syntax errors. So it can say, oh, if you use this macro, you should give it a term, not a more general expression. Another thing I'm finding has worked out quite nicely is using roles to extract common features or common interfaces of AST nodes. Some of those are things that sort of do exist more visibly at the language level. So for example, statements all do RakuAST statement, RakuAST term for terms, but others are sort of more involved in the semantic or declaration model. For example, we have RakuAST lexical scope, which is for anything that introduces a scope. We have lookup, which is anything that needs resolving. We have syncable, which is things that need to know if they are in a sync context, because they want to either give a warning, say, you put an integer in a sync context here, that's probably a mistake, or they want to compile differently, like the for loop. So let's move on and take a look at the progress that I'm making on implementing RakuAST. I'm glad to be supported in this work by a grant from the Perl Foundation, so thank you to them. And if your organization is in a position to support the Perl Foundation, that's a nice thing to do. They help make a lot of interesting things like this happen. A slight problem that I realized was going to come up as soon as I started working on RakuAST is that we really want the nodes to work as if they were written in Raku. But we need them in place in order to compile Raku code, because the compiler is going to use them as effectively its heart. So we really need to figure out a way to solve this circularity. Circularity is not a new thing. They're something that I have become quite used to when working on compiler things. And the Raku standard library already is kind of structured to help deal with this sort of problem. It comes in 3 parts. One of them is the meta model. This is meta classes. We write them in NQP, which is a subset of Raku. Meta classes say things like, well, what does it mean to be a class? How do we find methods? What does it mean to be a role? How does composition work? How do we type check things against each other? All those semantics live in the meta class implementation. And then we have the Bootstrap. That's more NQP code, and this pieces together basic Raku types. Things like scalar, attribute, things like routine, parameter, signature, and so forth. Really the types that have to be in place before we can start compiling Raku code, because the Raku code that we compile will depend upon them and use them. And then finally, we have the core setting, and this is where we implement the various built-ins in Raku already. And the ratio of code here is some thousands of lines of meta model, probably a couple of thousands of lines of Bootstrap, and then tens of thousands of lines of core setting. The vast majority of our standard library actually is written in Raku code. So where does RakuAST fit into all of this picture? Core setting we just already said is too late. It can't go there because we need the AST nodes in order to compile Raku code. They should feel like normal Raku objects. So the meta model should already be in place, which means that they really want to go here. And that makes sense too. They probably want to go towards the end of this because we already want to have various of the other types defined. So for example, they can inherit from any, which is the default Raku base class. But as I mentioned, the Bootstrap really pieces things together. We don't get to write classes with methods in there. We get to write really code which calls the mop, the meta objects, and says, oh, okay, please add this method to this class, and then add this attribute to this class. And the attribute has to be an object that we have put together, and this is all extremely slow going. It's not so bad because there's only so much of it that we had to do, but for RakuAST, it was going to be really, really tedious. Thankfully, I'm a compiler writer, and I said, okay, I know how to do this. And I wrote myself a little compiler, which takes a small subset of the Raku class and method syntax and turns it into mob calls. And those then get compiled into the Bootstrap. The other nice thing about the Bootstrap is we actually do this work at begin time, so that we don't pay for it every time that we start up. And it's just the same with the Raku AST nodes. So at this point, I have over 100 node types implemented. Some of those are abstract, so they're in the most extreme cases just markers. In many cases, they provide bits of functionality that are composed into the various other concrete node types. There's some hundreds of tests already covering the construction and evaluation of these nodes. So these cover the case where we synthetically produce RakuAST nodes. There never was any source code, and then we evaluate from the AST, and we never go via the source. And also, I'm working on creating a new RakuAST-based compiler front end. So you, at the moment, if you're on the correct branch, you compile this and then you set an environment variable, and it will choose the new front end instead of the current one. That at the moment is only so far along. There's quite a long way to go. It passes half the sanity tests, and the sanity tests are those things that we test in order to know that we have a chance of running or compiling test.pm. And that test module is then used in order to run all of the spec tests. If you want to follow the progress or try things out, the source of this is being developed and committed as they will go in the RakuAST branch of the Rakudo repository. If you want to try it out, you just put that environment variable in place and you're running the new front end. It's not very exciting yet, but it will at least work for some simple scripts. And you can follow my grant reports on the Perl Foundation blog. So let's finish up by taking a look at the impact of RakuAST on Raku language users. Firstly, I'd like to offer some reassurance. I'm quite committed here to making sure that for most people, when they upgrade their Rakudo compiler version, and for the first time they run a version of Rakudo that is based on RakuAST, they will not notice any changes to their program's behavior. That's quite a lofty goal, given that we are changing really a very significant amount of the compiler code base. However, there's some things that are decidedly in our favor. One of those is that we should pass the specification tests. This is a test suite that's been built up over around 15 years now. It's got well over 100,000 tests in it that cover all kinds of aspects of the language, and that should not show any regressions. For the places where the specification test suite has holes and it misses things, we then have another tool called Blin. Blin is used to test all the ecosystem modules against the head of Rakudo or against a branch. And that helps us make sure that we're getting even less regressions because then we're taking into account not just tests, but actually tests of code that users have written as modules as well. And that gives us really a much bigger corpus of code to compile. A few of those will be affected inevitably. There are some modules that have forged ahead of the current state of what is possible and have done the impossible instead by dealing with the compiler internals. That is not an API that's supported. Unfortunately, there'll have to be a few breakages there. I went and analyzed how many modules we can expect that to impact, and really we're looking at low double figures. And in terms of those which are actually in widespread usage, we're talking single digits. So getting updates of those modules available should not be too bad to achieve. The other thing is that actually this is quite nice, because in many cases we'll be moving these modules from dabbling in internals to using supported RakuAST APIs, and that's a very nice direction to be moving in. So I'm fairly confident we can keep the pain pretty low there. One other concern is that if we're adding this effectively extra layer, will we slow down compilation? And compilation isn't especially that fast at the moment anyway, so we don't really want to do that. At this point, I'm cautiously optimistic that even without a big push on this, we can come out ahead anyway. As I'm looking at the current compiler code and studying it as I replace it with the RakuAST implementation, I'm noticing that many times the better program representation that we're getting with RakuAST actually makes things easier. The best optimizations are when you don't have to do some work at all. And we save quite a bit of work. There's a lot of things in the current compiler where we build something and then we go back and we tweak it based on figuring out something else. And that happens in a few different places. Whereas I think with the architecture we'll very often just produce the correct cast tree in the first place. I think there's also potential for better optimizations. The static optimizer today is quite challenging to extend. There's occasions where we end up breaking it because we changed something and it was looking for a very particular cast structure and it doesn't find it, so the optimization doesn't happen. I think that will all become much cleaner with RakuAST as well. I've also been thinking a bit about parallelism, and if we can parallelize some aspects of compilation, and I think the answer is yes, we can. I've already got some ideas about parallelizing, for example, computing sync context. And given we have a runtime which is quite capable in the area of doing parallel computation, that's an opportunity we should look to exploit as well. So what next? Where from here? I think by early autumn this year, we'll have RakuAST nodes covering all of the language. In principle, that means that we're then done. In reality, life is never quite that straightforward. I'd say we should expect a couple of months of negotiating with the specification test suite and the modules and trying to make sure that we're not regressing things there. What about macros? Because surely once we have the AST, then we have most of what we need for AST macros. And I'd say, yes, we do. I think that it would be fitting to have those around by Christmas. Yes, this Christmas. And finally, then to have a language release that includes all of this, so it is formally part of a version of the Raku language specification in spring next year. So by the conference season next summer, I hope to be showing off a lot of the new things that you can do with this, and maybe we'll even be able to do that in person rather than virtually. But even so, it's been nice to be able to do this at all this year, given the situation we have. So thank you very much, and I'll happily take any questions that you might have.
Dakar, your hand is up. Go ahead.
Right. Jonathan, will there be a standardization or a definition, a proper sorry, will there be a proper definition of the pieces of the grammar for people to extend? Because at the moment I get the impression that about half the grammar used by Rakudo is very internal.
Okay, so there's a further step which would come after this one. And so one of the things that I mentioned about macros is that they largely are working on the basis that we parse something and then we invoke this compile time operation that produces some AST, and that lets us do all kinds of interesting semantic things. It doesn't really give us any fundamentally different syntax. There's another concept which is again only something that you really experimentally do at the moment, which is slangs. And the idea of a slang is it's basically a derivation of the language, and that is something that I've thought about, and I have decided that trying to pull that off at the same time or alongside doing the AST work is probably a bit too much. It would be preferable in my mind to deliver this and then spend some time on the slang work. So there's a good robust way to deal with doing syntax extensions and syntax changes. So yeah, it's something that's on my mind, but I sort of see that as a step after this. In some senses, I know a lot of people get really excited about syntax. I'm boring. I'm a semantics guy, so I'm having my fun first, and then we'll take a look at the syntax extensions too.
Well, knowing that it's coming at some point is good enough for me. Thank you.
Yep, you're welcome.
Hello.
Artenfels, you are unmuted. Go ahead.
So regarding macros, is there a way to intentionally defy the hygiene, or is that more like the very clean approach?
Yeah, there is a speculated pseudo package, which is called compiling, which basically would let you poke declarations into the scope that you are being called into, essentially the scope that we are, well, currently compiling. And yeah, I'm intending to implement that. I'm expecting a few dragons along the way, though, in principle, it should be the easy thing because it's the case where we don't have to do any renaming of symbols. Something tells me that there'll be at least a little bit of pain there, but yes, there is an escape hatch for that. And I think that's kind of important because sometimes you really do want a macro that will introduce something new into the scope of the place where the macro is invoked.
Thank you.
So in summary, yes.
Yeah, I've needed it before, so.
Mm-hmm.
Enormous, go ahead.
So question, this RakuAST format, or will it contain information about the original source so that we can use it as a format for editors, for instance, for syntax highlighting? And will it become tricky once macros are in place then?
Yeah, that's an interesting one. So what I've been thinking on that sense is that we kind of want two modes, if you like, of compilation here, or of parsing. One of them being that you really only want the positional information that you need to give good errors at runtime. So, the error occurred at this line number or this position. And then you also would want to have a way where you can say, well, actually, I'd like to have more information. I'd like to be able to recover a lot more detail about these things. And my current thinking, and this is provisional, is that there'll be effectively a provenance is my current name for it, attribute on the AST nodes, where you can say, well, how did we come about to have this node? And that would let you recover all of the extra information. And it's things like, if we have a quote construct, and we interpolate some things into it, we don't actually, at the AST level, really know what that code construct was. We don't need to know in order to compile, but for doing things like linting or syntax analysis, you would want to know that. So yes, the plan is to make it possible to obtain that and to keep it, but to also not enforce keeping it, because otherwise it bulks up the memory that's needed for the compilation.
Thanks.
Does anyone else have a question? Raise your hand.
This is Chris.
for
I
one.
can't raise my hand.
Oh.
May I
Oh,
ask
go
a-
ahead then.
Sure. Jonathan, Chris White, thanks very much. Great talk. My understanding is that Raku is still, the language is still whatever passes the spec tests. If that is indeed the case, is Raku AST being standardized to be included in RakuAST as part of Raku, or is it Rakudo specific?
No, the idea is to standardize it and to have it as part of RakuAST, as part of the specification. And that is partly why I'm designing this very carefully, and why I really felt that we needed to go through and carefully design something for that purpose, not just expose what happens to be in Rakudo at the moment. So yeah, it's aimed at the standard. The tests that I'm currently writing to cover AST construction will also be there. I think it kind of needs to be this way, because if it's not, most of the interesting macros I would want to write, the interesting traits I would want to write, depend on the AST. And if we don't standardize it, then we're making most interesting things be compiler-specific code, and that's what I want to get away from.
All right, thank you very much. Good to hear.
Yep, you're welcome.
Time for one more if someone has one.
Hi, great presentation. I was wondering what type of tree you're going to use. There's lots of trees out there.
Yeah, that's an interesting one as well. At the moment, it really is a case of each node knows its children. That's about it. It's not linked in any other direction at that point. I've kind of been around on the should it know about its parents as well. I've actually the tree that we have in the comma ID does do that. That has benefits, it has costs. The thing I've noticed is it kind of makes manipulations a little bit more tricky as well. So at the moment it's going as a top down, the parents know their children, and you can do various kinds of traversal that we provide of the child nodes. Also, there's not sort of a generic children array, if you like. Nodes actually, have attributes which hold the particular types of child node that kind of syntactic element has. So, an if statement node has a condition, it has some the then block, it has some branches, and so on. So it's not so freeform in that sense as the cache tree.